So in today's class, we will be doing a new topic, that is vector spaces. Okay, let me know when you're able to see my screen. Okay, we'll be talking about vector spaces. Okay, so what I want you all to do is to consider these two scenarios. Okay, we'll consider two scenarios. Consider these two scenarios. The first scenario is something which is very familiar. Okay, of course, both of the scenarios are familiar. So let's look at this scenario. Let us say I have a function. Okay, I consider a function f of s, function of s, and this function I'm writing as a linear combination of two other functions. Let's say I have one function phi1 of s. Okay, one function phi1 of s, and I have another function phi2 of s. I have another function phi2 of s. Then what I do is this phi1, these are two known functions. Okay, so phi1 and phi2 are two known functions. Phi1 and phi2 are two known functions, and these phi1 and phi2 are linearly independent. Okay, so here phi1 and phi2 are linearly independent. Phi1 and phi2 are linearly independent. Who can tell me what is the meaning of this term, linearly independent? Two functions are, if I say that these two functions are linearly independent, what do you mean by that? Can anyone tell me? Linear independence of two functions, what does that imply? Anyone? Anybody? Linear independence of two functions. Korabi, would you like to tell me? Linear independence of two functions. What do you mean by that? Mehul, can you tell me what is linear independence? Just the basic idea of linear independence.
Hello, sir. Sir, I can tell in terms of vector.
Okay, tell me in terms of vectors.
If vectors are orthogonal, then they are linearly independent, like in three-dimensional space, that they do not have any component.
Okay, good. That will work. So linear independence. Now here we are talking about functions. Okay, I'm glad that you mentioned about vectors, because I'm going to show a relation, a correspondence between this relation that I'm going to write here and a vector relation. Okay, so when I say linearly independent, what I mean by this is this. I'll give a formal definition of linear independence, but this is just to give an idea. So linear independence implies that phi1 cannot be written. Phi1 cannot be written in terms of phi2 and vice versa. Phi1 cannot be written in terms of phi2, and phi2 also cannot be written in terms of phi1. So in that case, example, let's say phi1 is equal to, let's say, s, and phi2 is equal to s square. Can you write down phi2 in terms of phi1? You can't do that, no? Can I write something like this? Phi2 is equal to some constant k into phi1? Not possible, right? So if you cannot write it like this, that means they are linearly independent. Okay, so this is the meaning of linear independence. Two functions are linearly independent if one cannot be written in terms of the other function and vice versa. So here we are assuming that phi1 and phi2, they are linearly independent. Okay, so what I'm going to do is I'm going to take these two functions. These are two linearly independent functions, and I'm going to get a linear combination out of this. So when I say linear combination, what I mean is the first function I multiply with a1, with some constant a1. Phi1 I multiply with some constant a1. Phi2 I multiply with some other constant a2. A1, a2 in general can be complex also, and I add them together. Okay, so this is a linear combination. So f of s is a linear combination. So f of s here, f of s is a linear combination of phi1 and phi2. F of s is a linear combination of phi1 and phi2. Let's call this equation number 1. Okay, now this kind of a scenario we also see this in, as Mehul has pointed out, in vectors, in vector way, because when I asked about linear independence, he gave the example of vectors. So in vectors also we see something similar happening. Okay, so consider this. Okay, let's say I have a vector a. Okay, say I have a vector a. Then how do you write down this vector a? How do you write down this vector a? So I say phi1 and phi2, and the example that Mehul gave was, if I have two unit vectors all along the x-axis. So along the x-axis, let's say the unit vector is x cap. You could call it as I cap also. Along the y-axis, the unit vector, let's say call it as y cap. Now we can always write a vector, right? This is basically what I'm doing. I have a vector. Okay, I have a vector. This is a vector a. So basically what I'm doing is I'm splitting this vector into two components. One is the component along the x-axis and another is the component along the y-axis. Another one is the component of the same vector along the y-axis. Okay, so this will have one component. This is the unit vector along the x-axis. This is x cap. This is y cap. So this vector that we have here, this is my original vector a. So what am I doing? I'm splitting this into two components. So this vector, I'm splitting it into a horizontal component and a vertical component. So this horizontal component will be simply ax into x cap. This horizontal component will be simply ax into x cap, and this vertical component is simply ay into y cap. So ay into y cap. Ay into y cap. Okay, so now this vector a, what are the different ways by which I can represent this vector a? One way is obviously this one, right? One way is you could represent this vector a as ax into x cap. This is one way, plus ay into y cap. This is one way to represent this. Another way by which I can represent this same vector a is, you already know what is x cap and y cap, right? Because these are unit vectors. These are already known. X cap, y cap, these are already known. So another way to represent this vector a is, instead of writing it x cap and y, ax into x cap plus ay into y cap, I can just remove this x cap and y cap and just write it as ax comma ay. Like coordinates, two different coordinates, ax and ay. We have two different coordinates. Just represent. Can we do that? Can we do it like this also? No problem, no? Because x cap and y cap, they are already known to us. So here we find a correspondence. Okay, here we find some kind of a correspondence. So the correspondence, here we have the following correspondence. The following correspondence, and the correspondence is basically this a1 that we have here, the small a1. Okay, the small a1, it does the same role. Okay, it does the same role as ax. Small a1 does the same role as ax. Similarly, small a2, it does the same role as ay. Small a2, it does the same role as ay. This is one correspondence that we are able to see. Next correspondence that we're able to see is this phi1, this function phi1 that we have. This function phi1 of s. This function phi1 of s, it corresponds to which one? this phi1 and phi2, they are already known, right? That's what I said. F is a linear combination of phi1 and phi2. So phi1 and phi2, they are already known to us. In a similar way, x cap and y cap, they are also already known to us. So phi1 of S, it corresponds to x cap. And similarly, phi2 of S, it corresponds to y cap. Okay. And finally, this function f of S, what does this correspond to? This function f of S, it corresponds to the vector A. Okay. So these are your correspondence. Okay. This is the correspondence between these two expressions. Is this clear? Is this clear? So what is this vector spaces? What is this vector spaces got to do with? I first of all use an example from vectors. Vector spaces, basically it extends the ideas from vector analysis to more general situations. Vector spaces, it extends the idea of vector analysis to more general scenario. In other words, the more general scenario that we're talking about is your functions. We extend the idea to functions. Okay, so this is what vector spaces are all about. We extend the idea of vector analysis to more general spaces. Okay, so now original two-dimensional space, we had an original two-dimensional space. The original two-dimensional space, what was the original two-dimensional space? The original two-dimensional space was, because we are talking about vectors. We are talking about a vector. What kind of vector is this? It's a two-dimensional vector. So original two-dimensional space is x cap and y cap, right? X cap, y cap. This is the original two-dimensional space. Then from this original two-dimensional space, we now go to a new two-dimensional space. From this, we go to a new two-dimensional space. Instead of x cap and y cap, we go to this new two-dimensional space, which is phi1 and phi2. Okay, so this is the new two-dimensional space. Okay, and this new two-dimensional space, this new two-dimensional space, it need not have anything. It need not have anything to do with physical space. It need not have anything to do with physical space. Because you see, in this vectors, okay, we have x cap and y cap. We know exactly what is x cap and y cap. X cap and y cap, these are two unit vectors. One unit vector is along the x-axis, another one is along the y-axis. We already know what this is. Okay, it's in two-dimensional space, it's in physical space. But this new two-dimensional space, that is phi1 and phi2, it has got nothing to do with physical space. It's got nothing to do with physical two-dimensional space. Okay, so just like how we had, so hence we can write down this original function, this function that we have, this function f of s. We had earlier, we had written this as a1 phi1 plus a2 phi2, because phi1 and phi2, these are already known to us. Because phi1 and phi2, they are already known to us, we might as well just drop phi1 and phi2, they're already known to us, and we can just write this function as a1 comma a2. That will also work. So this function f of s, we can describe this function f of s can be described in terms of this a1 and a2 only. The coefficients that you're multiplying with phi1 and phi2, just like how this vector a you are defining only in terms of ax and ay. We drop x cap and y cap and we define this vector only in terms of ax and ay. In a similar way, this function also we can define this in terms of, describe this function, not define. You could describe this function in terms of small a1, small a2. Okay, similar to how we write down this vector a as ax x coordinate and the y coordinate, okay, in a similar way. Okay, so these are your coordinate values. Okay, so these are, I mean, just like before, this and this, these are coordinate values. These are your coordinate values. Okay, a1, a2, and ax, ay. So these are your coordinate values. Is this clear? Is this clear to everyone?
Yes, sir.
Okay, so you need to keep in mind that this f and phi that we have written here, this f and phi, okay, even though I have written some independent variable s, okay, but in general this need not be s, it could be anything, okay, it can be x, it can be y, it could be some theta, it could be anything, okay. So what you need to keep in mind here is it's a function, this phi1 and phi2, this is a function of some independent variable, okay. Phi1 and phi2 are functions of independent variables, and we are using these functions of independent variables to construct some other function, which is f, okay. So here, equation number one, okay, this equation number one that we have written here, we write it like this. So here, equation number one, here equation number one defines, or let me type this out here. Here, equation one defines a function space that can be built from the basis. And which is the basis here? Our basis, just like your vectors, the basis is x cap and y cap. In a similar way here, the basis is phi1, phi2. This is the basis. Okay, so this is the basis. Phi1 and phi2 together. This is called as the basis. I'll give a more formal definition. Okay. Such a space is called a linear vector space. Okay, I'll refer to this LVS. Okay, such a vector space, such a space is known as a linear vector space. Why linear? Why is it linear? Because its members are combinations of the basis functions. Okay, so the space of all these functions, the space of all these functions f of s, all the functions f of s which I'm constructing using phi1 and phi2, this is known as a linear vector space. Why is it linear vector space? Because all the members of this vector space, such as f of s, we can build this using linear combinations of the basis functions. And which are the basis functions? The basis functions are phi1 and phi2. So using these two basis functions, various linear combinations of these two basis functions, we can obtain a linear vector space. Example, so let us say I choose, okay, very simple example, phi1 of s, it has to be a function of s, phi1 of s, as before, I choose this to be, let's say, s, and phi2, let us choose phi1 as s and phi2 of s to be equal to s square. Okay, so let us say I have a function. Let's say the first function f1 of s is equal to minus 3s plus 7 by 5 s square. You can immediately see Okay, you can immediately see here. In this case, minus 3s plus 7 by 5s square, this function. So here, wherever there is s, I could just replace this because s is nothing but phi 1, right? Phi 1 is nothing but s. So wherever there is s, I replace it with phi 1. And wherever there is s square, I replace it with phi 2. So you can see here, this f1 can be written as a linear combination of phi 1 and phi 2. Likewise, if I give another function, f2 of s, okay, what is f2 of s? Let's say some example, let's say 2.8 s minus 1.33 s square. So immediately you will see 2.8, it is equal to 2.8. Wherever there is s, you replace it with phi 1, and wherever, and on this side we have minus 1.33, and wherever there is s square, we replace this with phi 2. Okay, so this is one member. This is one linear combination. F1 is a linear combination of phi 1 and phi 2. F1 is a linear combination of phi 1 and phi 2. F2 is also a linear combination of phi 1 and phi 2. In a similar way, you could have any such function, lots and lots of functions. We could have lots and lots of functions. So this could be some linear combination, that is a n a1n phi 1 plus a2n phi 2. This is also a linear combination. So all of these functions which we are able to construct, using this basis. So this is my basis. It's a linearly independent basis, and all the functions that we have here, we can get each and every function using this basis. Okay, you can get each and every function using this basis. So this is my linear vector space, which is spanned by the basis phi 1, phi 2. So my basis is phi 1 and phi 2. This is my basis. So this basis, it creates this linear vector space. So this is the linear vector space which is spanned by this basis. Now, if I give you another function, okay, let's say some function g of s is equal to 3 minus 2s plus 7s square. Can you write this in terms of phi 1 and phi 2 alone? We have minus 2 phi 1, okay, and then we have plus 7 phi 2. That's fine, but there is a 3 here. See, there's one additional term. This additional term cannot be written either in terms of phi 1 or phi 2, right? Phi 1 or phi 2, we really don't know. So this one does not belong to this vector space. Okay, so this does not belong to the linear vector space spanned by phi 1, phi 2. Okay, so what is a vector space? Vector space basically is a set of functions. Okay, to put it simply, what is a linear vector space? A linear vector space is a set of functions. And what is so special about these functions? What is so special about these functions is each and every of these functions can be written in terms of the basis functions. Okay, that's your linear vector space. Is this clear to everyone?
Yes, sir.
Okay. So let me give some formal definitions which I have in my slides. So if you're asked to define a vector space, so what's a vector space? A vector space V over real numbers R or complex numbers C consists of a set of elements called vectors. So vector space it consists, like I said, what is a vector space? A vector space is a set, right? That's what I had mentioned, right? A vector space is a set. Yes or no? This is what I mentioned. In the example also, I showed you, right? This is a set, right? This is a set of functions. So what's a vector space? Vector space is basically a set. So a vector space it's a set of functions. Oops. So a vector space V, what is it? It is a set of elements. And what are these elements called? These elements are called vectors. Okay, just like I showed you. So we have, this is a set. Okay, this is a set. Okay, in this set we had one function f1, another function f2, another function f3, right? So each of these elements, this set of elements, each of these elements is known as a vector. Each element is known as a vector, and this is the vector space. Okay, this is the vector space. And how do you know that this is a vector? Very easy, because we saw what is f1. What is f1? F1 was -351 plus 7 by 5 phi 2, right? So what is f1? We can also write f1 like this, right? F1 is -3 comma 7 by 5, right? X coordinate, y coordinate, something like that. Similarly, what is f2? F2 is 2.8 minus 1.33, 2.8. So I could just write this as 2.8 comma minus 1.33. I could also write it like this, right? So these are just like vectors, right? So that's why each of these elements in the vector space, it's known as a vector. Is this clear? Is this clear? So remember here, when I say vector, okay, when I say vector, in general, when I say vector here, when I say vector, in general, we mean the function. We mean a set of functions. After all, this, if I say vector A is equal to AX, X cap plus AY, Y cap, this is also a function. It's a function of position. Okay, so in general, vector means we are talking about a function, any function which can be written as a linear combination of the basis functions. We mean functions that are linear combinations of the basis functions. So this is the meaning of the word vector. Is this clear?
Yes, sir.
Is this understood? Okay, good. So now that's the definition of the vector space. Now, what kind of operations can we do on vector space? There are two operations. One is the addition operation, another one is a multiplication operation. Okay, so addition operation, it is denoted by the plus sign. Okay, addition is commutative, that is x and y, x plus y is equal to y plus x. So in our example, okay, in our example, let's just take this. F1 is equal to -3 comma 7 by 5. So what does this mean? -3 pi 1 plus 7 by 5 pi 2. And let's say F2 is equal to, let's say 6 comma 6 comma minus 2 by 5. That is, F2 is equal to 651 minus 2 by 5 phi 2. Let's say this is the example. So one operation that you can do is addition. You see, this is a vector, right? This is one vector and this is another vector. F1 is one vector and F2 is another vector. So if I say x plus y, if I say x plus y, what are we actually doing? We are doing f1 plus f2. Okay, we are doing f1 plus f2. And what is f1 plus f2? -351 plus 7 by 5 minus 3 phi 1 plus 7 by 5 phi 2 plus f2. F2 is 6 phi 1 minus 2 by 5 by 2. And when you work this out, what do you get? Minus 3 plus 6 is 3 phi 1. 7 minus 2 is 5. 5 by 5 is 1 plus phi 2. Okay, so x plus y. But what if I do y plus x? Y plus x. Y plus x is f2 plus f1, and we know that it doesn't matter. Here also we'll get the same results. 3 phi 1 plus phi 2 here also we'll get. So the order does not matter. The order in which you add them does not matter. So that means if the order does not matter, it is commutative under addition. Okay. Next is it is closed under addition. It is closed, the space V is closed under addition. So what do you understand by closed under addition? What I mean by closed under addition is if x and y are two vectors and the sum of these two vectors, let's say we call it as z. Okay, so here x is this one and y is this. So what is z? Z is this. Is z also a member of the vector space? This is z, no? What do you have to do to be a member of the vector space? I should be able to write this function as a linear combination of the bases, right? So f1 and f2 I have added together and I got this 3 phi 1 plus phi 2. Isn't this a linear combination of phi 1 and phi 2 again? Yes, it is, right? It is a linear combination of phi 1 and phi 2. Okay, so this linear combination of phi 1 and phi 2, because this is a linear combination, that means the result x1, x plus y, if I add them, if the result is z, then the result is also a member. So if I take any two members of the vector space, if I take any two members of the vector space and I add them together, the result will also be another member of the vector space. Is that clear? X and y are two members of the vector space. This is one member, this is another member, and I added them together and I get this. This is also a member of the vector space. So adding two vectors gives us another vector in the same vector space. So this is the meaning of closed under addition. Okay, formally this is what you write for all x comma y belonging to the vector space. Okay, there exists z such that, okay, v, okay, I think I forgot what this symbol is, such that v in z equals x. V contains z equals x plus y equals y plus x. So okay, the sum, the addition, the result of addition of two vectors in a vector space, that result of addition will also be a member. So if that happens, then this is said to be closed under addition. Okay, that vector space is said to be closed under addition. Okay, next, it is associative. Okay, same property, associative. If I have three members, three vectors, x plus y plus z, first you add x, y plus z and then you add x, or whether you first add x plus y and then you add z, or whether you first add x plus z and then you add y, it does not matter. So that's why it's known as the associative property. Then there is existence of a null vector. There exists a vector called as a null vector such that if you add to x, if you add the null vector, you will get back the same one. So in our example, let's say we have f1. What is it that I should add with f1 so that I still get f1? What I should add here is the null vector. Okay, what I should add here is the null vector. And what is this null vector? This null vector is basically 0 phi 1 plus 0 phi 2. In other words, this null vector, the coefficients is simply 0 comma 0. Okay, so there's such a vector exists such that if you add that vector to any of the vector elements, that vector element remains unchanged. So this is the existence of a null vector. Then there is, apart from null vector, there is another vector called as a negative vector. Every vector will have a negative, okay, such that if you add to that vector, if you add its negative, then you should get the null vector, which was defined earlier. Okay, so a vector, I have a vector x, to that vector I add its negative, then this will give us the null vector. So in this example, so I have, let's say f1 is equal to minus 3, 5, 1. Okay, let me write it in component form. So F1 is equal to minus 3 comma 7 by 5. So what is the negative of F1? The negative of F1 will be 3 comma minus 7 by 5. Because if I add both of them together, I will get 0 comma 0. Because minus 3 plus 3 minus 7 by 5, sorry, plus 7 by 5 minus 7 by 5, both of these will become 0. So this is the null vector. So negative of a vector is any other vector such that when you add that negative to the original vector, you get the null vector. Then the other property is multiplication by a number. Okay, so vector space is closed under multiplication. That is, if suppose I have alpha, which is a real number, okay, and x, which is a element of the vector space, then multiplying alpha, the real number, with x will also give me another quantity which also belongs to the vector space. It is basically closed. So in other words, let's say I have here again, let's say f1. We have f1 here. What if I multiply 5f1? Then what will I get? 5f1 if I multiply 5 into f1. Here alpha is 5. Some constant I'm multiplying with to f1. So what will I get? So we'll get minus 3 into 5. We'll get minus 15. 5, 1. Then 5 and 5 will get cancelled. So we'll get plus 7 by 2. So this also belongs to the vector space. Okay, because this is also linear combination of the bases, so it also belongs to the vector space. So it does not matter whether you multiply or add to vectors, multiply with a scalar or add to vectors, the result will also be a member of the same vector space. It is associative. So suppose I'm having two numbers, alpha and beta. Okay, and these two numbers I want to add, I want to multiply with a vector x. So either you can multiply with beta, then you can multiply with alpha, or first you can multiply alpha and beta and then multiply with x. The result is going to be just the same. So this property is known as the associative property. It is linear. Okay, so suppose I have alpha. Okay, suppose I am having a vector x and another vector y, and I take the sum of these two vectors. I add these two vectors as per this operation. Okay, let's say I add these two vectors. After adding these two vectors, I multiply with some constant. This is the same as first multiplying with the constants and then adding them together. So this is a linear property. It is distributive. Suppose I'm having two numbers, whether I first add the number and then multiply it with the vector, or first I multiply the numbers with the vectors and then add the vector. So it's the same thing. So this is the distributive property. Then if I multiply 1, this is the identity vector. If I multiply 1 with a vector, okay, sorry, this is this if the number 1, if I multiply with a vector, the result remains the same. Okay, and subspace of a vector space is what is a subspace? Suppose I have a vector space, and from this vector space, let's say I carve out a smaller vector space. If that smaller vector space is also a vector space by itself, it is known as a subspace. So these are some definitions of the vector spaces. Okay, now we have concept of linear independence. Let's see how much time we have. Okay, we have 10 minutes, so I can just do this idea of linear combination. Okay, is this clear, everyone? Any questions you have? Okay, linear independence. A set of vectors is said to be linearly independent if the equation, this equation, okay, alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 and so on, alpha, okay, in general, any alpha you multiply with any vector, and if I suppose add them up all together, and if the result is equal to 0, the only way this is possible is if all of these alphas, if it is identically 0. If that is the case, if this is the only way by which you can satisfy this equation, then we say that these vectors, they are linearly independent. Okay, so an example of that will be, I'll take the example of, x cap, y cap, and z cap. Okay, so let's say I have x cap, okay, x cap, I have y cap, and I have z cap. Let's say we say that ax, ay, and az. Let us say that this is equal to 0. What conclusions can you draw? Is it possible that ax, ay, and az, all of them are non-zero? Is it possible? Definitely not. This is not possible. Why is it not possible? Why is it not possible? Let's assume that it is possible. Okay, all of them are non-zero. If all of them are non-zero, what does that imply? So we have a non-zero number plus some basis, some object x cap, another non-zero plus some other object y cap, plus another non-zero number into some object z cap. I'm adding all of them together and I'm getting nothing. So from something you are getting nothing. Okay, which does not make sense. Okay, so the only way by which it is possible is if there maybe let's say one of these is 0 and the other two are negatives of each other. Even in that case also it will not work, because let's say if ax is 0 but ay and az, they are negative of each other, but because y cap and z cap, they are perpendicular to each other, when I add them together, this result will be definitely not 0. Okay, so the only way by which this is possible, the only way by which this can be made possible is if ax, ay, and az, if all of them are identically 0. That's the only way by which this can be satisfied. So this is the definition of the linear independence. Okay, if this condition is not satisfied, if at least one of these coefficients, if it is non-zero, then we say that these are not linearly independent. Each of these vectors, this set of vectors, they are not linearly independent. Now coming to the idea of basis. What's a basis? We already know what the basis is, this phi1 and phi2 that I had shown over here. Now a more formal definition. A basis is also known as a coordinate system. Just like you had x cap, y cap, z cap, that's your basis. We could also refer to that x cap, y cap, z cap as a coordinate system. A basis in a vector space V is a set of vectors. Okay, this set of vectors is phi1, phi2, phi3, and so on, such that every vector in V can be written uniquely as a linear combination of the elements in phi. So this is exactly what I had told you. I have a vector space, and that vector space is spanned by some basis phi1, phi2. Okay, then every element in this vector space V can be written as a linear combination of these elements. That is a1 into phi1 plus a2 into phi2 plus a3 into phi3 and so on. That is going to give me each and every element of this vector space, each and every capital phi. Okay. Okay, so such that for all y belongs to the vector space, there exists one and only one set of numbers which satisfies this relation. So suppose I have a member y in this vector space, then you can only find one set of numbers, eta1, eta2, and so on, which satisfies this equation, that is y is equal to eta1, phi1, eta I, phi I. Okay, by the way, are you all familiar with this notation? This is known as the Einstein's summation convention. Einstein's summation convention. So here I is a dummy index. I is a dummy index. So therefore this means the summation over I is implied. Summation over I is implied. Okay, so when I say eta I phi I, this is a dummy index because it has been repeated. Because it has been repeated, that means the summation over I is understood. That means this is the same as eta I phi I, and the summation is carried out over this small I. Okay, so it means this y, when moment I write y as eta I phi I, it is understood that this y that we are talking about, it is equal to eta 1 phi 1, eta 2 phi 2, eta 3 phi 3, and so on. Okay, so a unique set of basis elements is such that any vector in this vector space phi can be written in this way, that is satisfies this condition. Okay, there's an example using the Legendre polynomials. It's almost time. I just have 3 minutes left, so let me stop here, and I'll see you all 1 o'clock. Okay, at 1 o'clock. You all can give your attendance for this class. Okay, at 1 o'clock I'll